Okay, we're going to look at exponential applications, starting off with exponential growth or decay. So we use exponential functions to model situations where the dependent variable changes, it could be increasing or decreasing, by a constant factor for each 1 unit change in the independent variable. So let's take a look at number 1 and see how this works. We have Ashley. She's graduating from college. She took a job, starting salary of $40,000. She can expect a 6% raise in pay each year. Okay, so this is yearly. Compute her salary for the first 4 years. So she starts off, so year 0, so she hasn't worked there a full year yet. She gets a salary of $40,000. Year 1, to calculate her new salary, we would take her original salary, then we would add her raise. Well, she's getting a 6% raise, so to figure out how much of a raise she's going to get, we're going to multiply 0.06 times 40,000. Now doing that, we will get her new salary with the 6% raise. Now there's a little formula here for calculating this, and in order to come up with this little formula, we're going to go ahead and take this process right here and we're going to rewrite it. We're going to rewrite this expression by factoring out something that both terms have in common. So both of these terms have 40,000 in common, so we're going to factor out a 40,000 out of both. Okay, so if I factor a 40,000 out of 40,000, I get 1 plus, if I factor out a 40,000 out of this one, I get 0.06. Okay, and then your time is going to be your exponent. So let's see how this works. Turn it on. So we have 40,000 plus 0.06 times 40,000, and so her new salary is going to be 42,400. That's doing this first one. Okay, now let's take a look at this one where we factored out the 40,000 and see if it gives us the same. So 40,000 times 1 plus 0.06 raised to the, and in this case t is 1 raised to the first power. And notice we get the same answer. And this is a growth. This is the growth rates right here. The 0.06 is 6%. That's the growth rate. Okay, we have a growth. We're adding to our original amount. So salary, $42,400. Nice raise, Ashley. Second year comes along, and we're going to use our formula here. We're going to start with our initial. We started off with $40,000. One plus 0.06. This time is 2 years. Okay, so now I'm going to go ahead and put this in my calculator, and this time I'm going to change it to 2. So this second year she will be making $44,944. Forgot my $sign. Okay, Go ahead and find out the next 2 years on your own. It says write a function for Ashley's salary after T years. Okay, so it's going to be 40,000, her initial salary, times 1 plus 0.06, or you know what, better yet, since that stays the same, what's 1 plus 0.06? 1.06 raised to the t power. Oops. So, in order to find Ashley's salary in terms of t, we would use this formula right here. Again, the A value is your starting amount. She started off at $40,000. Since it's greater than 1, it's a growth. Remember, growths are any base greater than 1. The growth rate is 6%, and T is your time. It says graph the function for 0 to 30 years. Okay, so let's go ahead and count by 5s. Since time is independent, time's going to go on the x-axis. I think I went a little bit too far. Oh well. A little longer. And let's see, 40,000. Let's go by 20s. Sure. 20, 40,000. So I'll put a K. K is for 1,000. 60,000, 80, 100, 120, 140. All right. This is her salary. And this is her time in years. All right, so we could plug in 5 in for T and then get her salary and plot that amount right here. We could do that. Or we could go to our calculator. We could do it in our calculator. We could plug in the formula here, which I have already plugged in. So at 5 years, we're at $53,529. Somewhere in here. Remember, in 0 years, that's when she began. She's at 40,000. Let's see, 10 years. Let's see what our calculator says for 10. So in 10 years, she's got 71,634. 15 years, 95,862. And I wish my salary went up like hers. I'm not drawing this very well. It'd be better if I was actually on a grid. Anyway, you get the idea. It's going up. It's going to go up exponentially. Something like that. Okay, so 10 years, we could use the table. 10 years, 71,634, and don't forget the 91 cents. Notice in here it truncates at the decimal. Actually, it rounds. See, it ends with a 4. This one ends with a 3. It actually rounds it to the nearest whole number. So $71,633.91. Go ahead and calculate this one for me for tomorrow or for Monday. Now, when will Ashley earn $60,000 a year? Well, now they give us her salary and they want us to find the time. So, salary represents your Y. So let's take a look here. If I was going to graph this on here, I'm going to need to change my window. We want to go to $60,000. So we're definitely going to need to have a Y max of, say, 80,000 to go a little higher than 60. We wouldn't have a salary less than 0. Years, 0 years to, let's say, I don't know, 20 years. Scale is good, 0 to 20. But this one, I think I'll change that one to 500. Count by 500s. Let's see what we got. All right, we want $60,000, so go to Y equals, and then you would plug in your 60,000. Okay, and we want to see where they intersect. So second, trace. We're looking for their intersection. So we put our cursor near the intersection point, and we press enter 3 times. 1, 2, 3. So it looks like it's going to be, to get $60,000 salary, it's going to be about almost 7 years. So approximately, I'm going to go ahead, and since she doesn't get her salary until I believe the year is up, I'm just going to go ahead and do 7 years. Wow. What's wrong with me? There we go. Okay, let's turn the page. All right, here's the model for exponential growth and decay. Again, we've talked about this already. Here, this is going to represent your amount, your ending amount at time t. This is your initial amount. How much did we begin with when time is 0? Okay, your base is going to be either a growth or a decay. It's a growth if it's 1 plus, like we just saw with Ashley, was 1 plus 0.06. It's going to be a decay when it's less than 1. So if I did 1 minus 0.06, that would be 0.94. which is less than 1. That's a decay. R is going to be your rate of change, and then T represents time. We'll see R a little bit later. Okay? That R represents this, your growth rate or your decay rate. Okay? Rate of change. Let's take a look at number 2. If you drank 1 soft drink, the formula for the amount of caffeine in milligrams left in your body after 2 hours would be this. So, we have an initial amount of what? What is the rate of change as a percent? How much caffeine is the... I want you to try to answer number 2 for Monday. Try to do all of this information right here, based on what you've learned so far. And we'll pick it up in another video Monday night with half-life decay. Hope you guys are having a good weekend.